We are Robotics for Space Exploration from the University of Toronto in Toronto, Canada.
For URC 2025, we have made major upgrades to our rover to help it complete this year's tasks.
For this year's chassis, we prioritized a lightweight and adaptable design with a carbon fiber base plate that will provide a smoother framework for the mounting of subteam-specific modules. Each module to be mounted is constructed from an aluminum extrusion frame to allow for ease of assembly and implementations for future iterations. For the suspension system, we have transitioned from last year's wishbone suspension to a four-wheeled rocker system with a differential bar at the back of the rover.
The rocker is made from carbon fiber tubings and pivots with a steel axle. This design has allowed us to achieve a lightweight, compact, yet strong and robust design. The wheels are 3D printed in two parts with an outer layer made from TPU with a gyroid pattern to evenly distribute deformation and an inner rim printed in PLA+. We have built upon last year's wheel design and made substantial improvements to the durability and ideal absorption in the rough terrain.
Having refined our power architecture last year, we've had the opportunity to develop in-house solutions that better fit our requirements.
This year, the rover boasts a larger battery, giving a drive time of more than 2 hours. Replacing the pouch-style batteries with cylindrical cells yields better handling and electrical safety. This year's BMS system relays important parameters back to a GUI at the base station and to a display located on the rover. This GUI also allows for manual control of the status LEDs and power cycling of various voltage rails for easy debugging and allowing us to remotely stop the rover. Finally, many converters on board the rover have been designed in-house. A significant addition has been our gallium nitride-based onboard charger. This converter is able to charge the rover while it's running, making for unlimited testing time.
This year, we have taken what we learned from URC 2024 and revamped our software stack, starting with a custom GUI that will centralize controls and visualizations during autonomous tasks. It displays camera feed, interacts with the state machine for status, and acts as a control center for manual traversal. Our new GNSS antennas have significantly enhanced their positioning capabilities, achieving sub-centimeter accuracy in position and heading using RTK. We have also developed a custom navigation package which includes localization by fusing GNSS with visual odometry and magnetic heading through an extended Kalman filter. Octomap is used to map our environment, A-star algorithm is used for global planner, and obstacle avoidance is conducted with a dynamic window approach local planner.
This was tested using our new Unity-based simulator, which has over 100 square kilometers of real-world topology terrain to test our algos and techniques. We use 2.4 GHz antennas for comms to improve bandwidth and control the rover up to 1 kilometer. For identification, we use our Z camera to facilitate computer vision, reading Aruco tags in complex environments. To detect objects, we custom-trained a YOLO V8 model to discern both mallets and water bottles with great accuracy.
This year we made our arm lighter and stronger than ever before. We have removed the belts on our arm, which improves its lifting capability as there is no more belt slippage, as demonstrated by lifting up a 5 kilogram weight. Many links have been redone with forged carbon fiber to further reduce weight and increase strength. Our end effector consists of swappable fingers, allowing for on-the-fly changes. Current end effector is capable of picking up rocks, flipping switches, and interacting with dials. Our inverse kinematics code allows for fine Cartesian control of the arm, and a newly developed GUI simplifies control. ARM software has been busy developing an autonomy stack using MoveIt and Octomap, which has tested and verified in Gazebo. This year, the ARM will help science team collect soil samples. The wrist can be swapped with a drill bit to collect samples, and an array of deposit zones are placed on the rover for science team to perform experiments in.
The science subteam has redesigned several elements of our payload, including our coring drill bits, which are now made out of steel pipe and tested to ensure durability. Our 12-centimeter cache bit can be opened by hand, revealing a complete core. Surface samples from 2 sites are delivered to the FAD fluorescence and chemistry modules, dispensed using auger-based mechanism. 9-hydrin is used to test for amino acids in soil, with results visible over webcam. A new pH probe measures the soil pH. Our FAD fluorescence test now includes a blue laser, a buffer solution, and lens added to increase observable fluorescence, and a combination of a lens tube, 3 bandpass filters, and a reflective cover to ensure that our photomultiplier tube is shielded from all natural and laser light. Temperature, moisture, and humidity sensors are placed into a probe that transmits data to the rover via Bluetooth. A microscope camera is also used to examine grain size and other fine details of rocks. Finally, our multispectral imaging system allows us to identify minerals in rock faces that would previously have been inaccessible. The system features a monochromatic camera with sensitivity in the IR range and a series of 12 distinct bandpass filters.